See, a system is said to be causal. Suppose it is a system with input x of t and output y of t, and h of t represents a unit impulse response. This system is said to be causal if h of t is a causal signal. This system is a causal system if the unit impulse response of that system is a causal signal. What is causal signal? H of t is equal to 0 for t less than 0. For t less than 0. It is existing in the right side only. After t is equal to 0 only. Then you can say that it is a causal system. So, a causal system is a system for which the unit impulse response is a causal signal. When do you say a signal, any signal is a causal signal? Suppose you take any signal x of t. That x of t is a causal signal if the value of that signal is equal to 0 for t less than 0. It is existing for t greater than or equal to 0 only. Then that signal is called a causal signal. Okay? If unit impulse response is equal to 0 for t less than 0, then it is a causal signal. Next, stable system. An LTI system is said to be stable if the unit impulse response of that LTI system is absolutely integrable. If the unit impulse response of that system, that is integration minus infinity to plus infinity mod h of t dt is less than infinity, then the system is said to be stable. See here, in some questions, a system will be given. A system will be given, and whose Laplace transform will be given. And how do you find whether the system is stable or causal? You just find a unit impulse response by finding the inverse Laplace transform. By finding the inverse Laplace transform. Finding the inverse Laplace transform, then you will get a unit impulse response. Now you check that h of t is equal to 0 for t less than or less than 0. If it is equal to 0 for t less than 0, then the system is causal. And you check whether it is absolutely integrable or not. Then the system is stable. Here, why I explain you these concepts here in the Laplace transform subject. These two concepts are very important in order to find the inverse Laplace transform sometimes. Generally in gate examinations, what happens, a system with the transfer function h of s will be given. Then the question is that find the inverse Laplace transform for that signal. Find the unit impulse response for that signal, provided some conditions are given. It is a causal signal, it is a causal system, it is a non-causal system, it is a stable, and it is not stable, like that. Depending upon those conditions, you need to find the unit impulse response. How do you find unit impulse response? By taking the inverse Laplace transform. When you find the inverse Laplace transform, what information do you require? The ROC is also required. But ROC is not directly given in the examination. The ROC is not directly given. But the system characteristics are given. According to the system characteristics, you have to obtain the ROC characteristics. So after getting the ROC characteristics, based upon that ROC information, now you find the inverse Laplace transform for h of s, that is unit impulse response. See here, suppose h of s is given. If h of s is a causal system, then what information is available with ROC for this system? Suppose h of s is given. It is a causal system. That information is only given. If it is a causal system, then you know that the unit impulse response is a causal. Then h of t is equal to 0 for t less than 0. Then it is a right-sided signal. If it is a right-sided signal, what about ROC? ROC is also right-sided. That is, sigma is greater than a pole. Sigma is greater than rightmost pole. Like that. So this information is obtained from this condition which is given in the examination. And suppose in the examination it is given like this: the system is stable. HFS transfer function is given, and one information is given, that is HFS is that system is stable. Find the unit impulse response. If HFS is given and it is stable, then if it is stable, what information is available? It is absolutely integrable, no? It is absolutely integrable. When it is absolutely integrable, you just observe that what we have discussed initially. If any signal is there, except is there, if it is absolutely integrable, then the Fourier transform for that signal is existing. So, if h of t is absolutely integrable, then the Fourier transform for h of t is existing. The Fourier transform for h of t is existing. The Fourier transform is existing or not, how do you represent, how do you find in the ROC of Laplace transform? In the S plane, we have discussed that on the j omega axis, the Laplace transform is equal to Fourier transform. No? The Laplace transform is equal to Fourier transform. If ROC includes the j omega axis, then the Fourier transform is also existing. Otherwise, the Fourier transform does not exist. If ROC includes the j omega axis, that Fourier transform for h of t is existing. If Fourier transform for h of t is existing, it is absolutely integrable. Then the system is stable. If ROC of j omega axis does not include, then it is not absolutely integrable. Then Fourier transform for h of t is not there, then it is not stable.